Hello everyone, this is Dr. Fang. This week we will learn chapter 9, linear momentum and collision. Okay, so this chapter we talk about another very important theorem, and use that theorem we can solve. Well, the theorem is momentum and impulse theorem. Okay, another theorem from Newton's law, and use that theorem we can solve um, a special kind of situation. It's called collision. Okay. In this chapter, we talk about linear momentum. So in physics, concept is really important. So we have to know what the exact momentum is. And this momentum actually comes from Newton's second law. Other than that, we will learn impulse, another new concept, and we will learn impulse momentum theorem. Another very important theorem. So last chapter we learn work energy theorem, right? So this chapter another important theorem, impulse momentum theorem. And under certain condition we have conservation of momentum. So last chapter we learned conservation of energy. Energy conserved under certain condition, and then same thing here, momentum conserved under same condition. Okay, so conservation of momentum. By the way, all the momentum, all the stuff here we learn is linear. Uh, so we learn this kind of motion. Basically it's a linear motion. Object move from one position to another position, right? Even it's a curved line, it's still linear. Next chapter we will learn different kind of motion. That is rotational motion. Okay. And for collision, then after that we learn collision. Collision we have inelastic collision and elastic collision. So what is different kind of those collisions are. Uh, so what is inelastic collision and what is elastic collision? Uh, After that, we will learn center of mass, another very important concept, and how to calculate the center of mass. Uh, then we talk a little bit about how the rocket propel in space. Okay, and the other one is from momentum theorem. All right, first things first, let's see what is linear momentum. Momentum is a vector. So this is a vector. You see there is a arrow bar on top of that. Momentum is a quantity, bundle mass and velocity together. So if something with mass move with velocity, then momentum is mass times velocity. For mass and velocity, because velocity is a vector, so this is a vector, so momentum is a vector. So suppose you have a mass and this is a velocity, right? So what's the momentum? Well, momentum equal to mass velocity, right? So momentum will be this vector. Momentum is in the magnitude of momentum is mv. Okay, so that's a magnitude of momentum. Direction same as velocity direction. Okay, assume this is this object with 2 kg. Okay, velocity is 4 meter per second, right? So momentum is 2 times 4 equal to 8 meter kg meter per second. Okay, so the unit for momentum is kg meter per second, and the direction, whatever velocity direction is, maybe this is what northeast, right? Okay, so momentum will be in the same direction as velocity. Okay, all right. So that's momentum. So if I ask you, there is something will hit you, but you have a choice. Um, what kind of object hit you? Um, you have a choice, right? So what is your choice? You want to hit by a heavy object or a light object? Most people will choose light object. Well, the answer here is you want to hit by something with smaller momentum. Okay, so here's a bullet, right? Only have a few gram, 10 gram, right? But a bullet move with 400 meter per second. Okay, so momentum of this bullet is, well, 0.01 kg times 400, right? So this equal to 4 kg meter per second, right? So that's the momentum. And if you have a heavy object, maybe 2 kg, right? But this one move with a very small velocity, right? Maybe 0.1 meter per second. Okay, just consider there is a rock, right? With a 2 kg rock, kind of slowly move towards you. And in this case, momentum, so this is P1, this is P2 equal to 2 times 0.1 equal to 0.2 kg meter per second, right? So you would rather choose something with less momentum to hit you, okay? So not only about the mass, actually it's a combination of mass and velocity. So you're here. This is you, right? So which one you like to choose to hit you? Well, you choose the one with a smaller momentum. Okay, that's the concept of momentum. Now we talk about the changing momentum. Changing momentum. Well, remember momentum is a vector, right? So this is mv, right? So what's the meaning of changing momentum? Changing means P2 minus P1, right? So this equal to mv2 minus mv1. Or you can write mvf initial. That's the meaning of changing. Okay. So you always, because remember velocity is a vector, right? So when we deal with a vector, you always need to define a direction. Okay. So if it's one-dimensional, you have to look at the direction. Okay. So direction sign actually tells you direction. All right. So let's see the example. The example here is there's a muddy bear, right? And then initial velocity is this, and then when drop to the ground, this is the final velocity. Okay, well actually muddy bear just sit on ground, doesn't bounce back. So in this process, what is changing momentum for this muddy bear, right? Changing momentum equal to mvf minus mvi, right? And well, this is a one-dimensional problem. And then we assume this is your y-axis, right? And then final momentum, final velocity v equal to 0, right? For vf, right? So this is 0 minus m initial momentum. This is a v, however, it's point down, so that is negative v. Remember, direction sign here tells you the direction. And if you work on this problem, right? So this is 0 minus negative 0 minus negative mv, right? So minus negative means plus positive. Okay. So that is remember this one is tells you the direction, tells you the magnitude of velocity. Okay, so just like this, muddy bear drop down with 20 meter, assume, right, 20 meter per second down. Okay. Okay, assume this muddy bear is 3 kg, assume. Okay, so equal to 3 times 20 equal to 60 kg meter per second. Okay, so this is the changing momentum for this muddy bear. What's the changing momentum for this object? Well, this is an elastic, like a mm, well, something. Well, when you somebody play with a Super Bowl, right? Just like you drop something with, assume here 20 meter per second, right? And when this object hit the ground, right, then the object will bounce back with this velocity 20 meter per second, right? Bounce back with the same velocity. All right, so in this process, what is the changing momentum? changing momentum equal to what? Final, right? So assume this is the same thing, 3 kg, right? So equal to 3 kg time, well, let's see, one more step. What is the final velocity? Okay, same thing here. This is your y-axis, right? Final velocity is a positive value. So that is mv. Initial velocity, this equal to m initial velocity v down, okay, so negative v, okay, so this equal to if you move together 2 mv, right? So same thing here, final momentum, right? Final momentum equal to 3 kg times 20, okay, 20 is positive, right? Initial momentum is 3 kg times 20 down negative 20, okay, so this is a changing momentum, okay, so 60 minus negative 60, right? So plus 60 equal to 120 kg meter per second. So when we calculate the changing momentum, remember momentum is a vector. You have to consider the direction of the velocity, okay, then you can make the changing momentum right. All right. Well, after we understand what exact momentum is, then we can go back to revisit Newton's law. Newton's second law states that net force equal to ma. Okay. What is a? Right. So we go further substitution. Right. A is changing velocity divided by changing time. Right. And the changing velocity equal to Vf minus Vi divided by changing time, right? And one top you see here, this is final momentum. Well, if you let the mass times the velocity, right, then this is a momentum. So momentum minus initial momentum divided by time. So this equal to changing momentum over time. So net force actually, in a general way, is changing momentum over time. Okay, that's a net force. Actually, this that is Newton's second law. So in more general, Newton's second law present in this way. It's a time rate of changing momentum. Net force equal to the time rate of changing momentum. Okay, by this, if we use this equation, then we can solve the problem with changing mass. Mass not necessarily always the same, right? So sometimes you have changing mass. In that case, by using this equation, you can solve the changing mass, solve the problem with the changing mass. Okay. All right. So that is the first concept. It's momentum and momentum with the Newton relationship between momentum, changing momentum, and Newton's second law. Next concept we will learn is impulse. So what is impulse? So if you look at Newton's second law, right? So this equation. So what do we do here is net force equal to changing momentum over time, right? And then both sides you times the time. So net force times time equal to changing momentum. Okay. So this term, okay, is defined as impulse. Okay, that is impulse. Impulse defined as, you see, left side, force times time. Okay, well, actually, is this force, right? So the net force, we can always use an average force to represent this net force. Not all the process have exactly same constant force. Okay, a lot of process you have a variable force. So we can always use average force to represent that average force, to represent that force. So force times time is definition of impulse. Okay, so first let's talk about a little bit about impulse. Impulse, because force is a vector, So impulse here is a vector. So you have direction and magnitude. What do I mean about the changing force? Very simple. Suppose you have object drop to the ground, right? Okay, so this object drop to the ground with V. This is M, right? So if we look at the force, net force on this object, right? Well, actually, let's look at the force, just the force and the time. Okay, so what happened to this object, right? Object moving down, right? Moving down, then almost touch the surface, right? Touch the floor. Okay, and then if you have a high-speed camera, you can see the shape change of object. Then more shape change of object, right? Then less shape change, then object will leave the ground. Okay, so this is time axis, right? So that is from here, objects almost touch ground. Here, object almost leave the ground, right? So from here to here, there is an interaction between object and the ground, right? So if we look at the interaction between the object and the ground, so this is interaction between the object and the ground, right? I like to use tennis ball in class, so just assume this tennis ball. Okay, so time here, right? If we start time here, nothing. There's no interaction. Object does not touch the ground, right? So no interaction. Then object touch the ground, right? And then more touch the ground, right? Then shape change, more shape change. Shape change actually corresponding to the force between them. Okay, maximum phase change, right? Shape change, then less, right? Then object leave the ground. Okay, so that's the from here to here. That is the interaction time between object and the ground. Okay, so this force, right? So this force is a changeable force. Okay, right? And then how to represent, so the time here is delta t, right? So delta t and the force between the tennis ball and the ground. So that is this, right? With time. So however, the force here is a changeable force, you see, change. And then how to calculate impulse. Impulse calculated this way. So this is because this is a changeable force. And then force times time. This is the area underneath of this curve, right? So we can find some sort of average force because this is a changeable force. We don't know exactly it is. Just let's use average force so that average force times time equal to this changing force. Let's put everything here times time. Okay, so this is area underneath the curve, and then we use this average force. So the area, right, under. Okay, so this is the area of average force and time, right? So as long as those two areas are the same, which means you use average force to represent that interaction. Okay, so you have same momentum, same impulse. Okay, so that's why we use an average force to represent this changing force. Okay, to calculate impulse. Unit for impulse here is, you see, Newton times time, right? So it's also equal to kg meter per second. Newton actually is kg meter second square, right? So mass acceleration, right? And then times seconds, right? So second cancel one, so you end up with Newton meter per second. All right. Remember, impulse is a vector. So the direction of impulse actually direction same as direction of the force. So in this example, okay, so tennis ball hits ground. What is impulse from ground on tennis ball? We know ground provide force towards the tennis ball, right? So the force is in upper direction. So the impulse is in the upper direction, right? So equal to average force times time. Actually, this is the force, right? Average, you have to find the average force to represent this variable force, and then average force times time, okay? By the way, we know for this time, tennis ball hit the ground, the time is very short. Interaction time is very short, maybe only 0.2 seconds, okay? That's the meaning of impulse. And well, from that equation, right? From impulse, right? Equal to average force times time, right? And also we know that is equal to and from average force times time, right? And that is changing momentum. Okay, so that's before we learned, right? Because if you divide by this to this side, that is average force. Average force also equal to changing momentum over change time. Okay, so if we link that way, we can tell impulse equal to the changing momentum. Okay, so this is called impulse momentum theorem. Okay, so this is impulse momentum theorem. Why you have a momentum change? Because somebody provide you impulse. Impulse actually is force and time. So if you bundle force and time together, that is impulse. And the consequence of impulse is momentum change. Okay, so this is the impulse momentum change theorem. So now let's look at an example. Suppose you have a baseball, right? And the baseball move towards this batter, right? And then the batter use this better bat this ball. So baseball move to this direction, right? So this initial impulse, initial momentum P1, PI, right? And then PF. Okay, so you can tell you have a changing momentum. Okay, so that's the changing momentum of this baseball. Why this baseball got changing momentum? Because somebody gave this guy an impulse. Okay, and the impulse equal to the changing momentum. Who gave this guy impulse? Who gave the baseball impulse? This guy, right? Use this bat, right? And then bat provide a force, and there is an interaction time. Interaction time can be very small. Okay, so impulse equal to FAV average force, right? Times time. Time is very small, very short, right? So the force here is big. So from calculating, by calculating the changing momentum, right, we can figure out what is the magnitude of impulse. And if we know the time, then we can figure out this average force. Assume example here. I don't know the mass of the tennis ball. Maybe give this 50 gram, right? This speed here. What's the speed of baseball? Well, let's make it up, right? 40 meter per second, right? Same thing here. 50 gram here baseball, right? And then 60 meter per second. Okay. This is the final. And then let's see, assume the contact time, baseball and the bat contact time is 0.20 second, okay? We want to figure out what is average force. Okay, so just do this problem. Well, we we know based on impulse momentum theorem, impulse equal to changing momentum, right? Impulse here is average force times time. Changing momentum is mvf minus mvi. Okay, let's make this direction a positive direction. Okay, so we plug in data. When you plug in data, remember you have to make sure to use the vector. So there is a vector. So you have direction associated with it. You have to use the sign to tell the direction. So average force, right? Times time here, there's a 0.2 seconds, right? Mass, 50 gram. Okay, 0.50. Final velocity here, right? So this is final velocity, 6 meters per second, and it's in the positive direction. So times 60, okay, minus 0.05. Initial velocity, 40 meters per second, negative 40, right? It's point to the negative direction, so negative 40. We make the calculation. 5 times 60, 0.505, right? So this is 3 minus negative 2.0, right? So FAV equal to what, 60, 3, 5, right? 5.0 divided by 0.2. So this equal to what? 25.0 Newton. This average force, okay? Well, if the time even shorter, then you have a bigger force, right? All right, so this average force. So average force can be big or small, depends on the contact time. Okay, contact time is short, then the force will be big. Contact time is bigger, then force will be small. The consequence, right? So this is the consequence of this impulse, and you can tell the force is positive, which means the force will be in this direction. Okay, this is in the direction of the bat hit the baseball. Okay, right? So that's how you calculate the average force. And if we give you average force, and then you can you can calculate what's the time, right? So for this equation, give you some known, and you can figure out unknown, right? So if we give you impulse, you can figure out final velocity, right? Or give you force, you can figure out time. Okay, that is the impulse momentum theorem. Now let's talk about conservation of linear momentum. So what does that mean? Okay, from Newton's second law, we know net force equal to this term, right? Changing momentum. Well, if net force is 0 to an object, then changing momentum over time is 0, which means changing momentum is 0. Okay, because time period cannot be 0, right? So this is not 0. So changing momentum is 0. Changing momentum is 0 means final momentum minus initial momentum is 0, and which means PF equal to PI, right? So momentum is the same before and after. That's the meaning of momentum conservation. Well, momentum conservation happens under one condition: net force equal to 0. Okay, and this net force can be on an object or can be on multiple objects if you consider this object as a system. Okay, So if you group several objects into a system, okay, so this is a system, right? If net force on this system is 0, well, what happened to those three? Assume this system you have three objects. Okay, those three objects can interact with each other. However, there's no force outside of this system apply on those objects. Okay, so M1 and M2 can bump to each other. M2 and M3 can bump to each other. Bump to each other means you have interaction. Okay, so they can interact with each other. Well, if you consider those three as a system, okay, so the interaction within or between them doesn't count as the force from outside. Okay, so here we talk about the internal force and external force. Internal, external. External means the force from outside. Internal means the force inside, within. Okay, so just like this. If you have three objects, right, and you group those three objects as a system, then if they interact with each other, that's okay. This kind of force is internal force. If you add all the internal force together, it's always equal to zero. Reason for that is assume you have a system M1, M2, right? So you only have two objects within a system. However, they interact with each other. Okay, so M1, assume M1 and M2 bump to each other, right? So that's interaction. During that interaction, M1 provide a force to M2, right? Meanwhile, M2 provide a force to M1 if there is an interaction between them. Okay, still this is the system. Those two forces actually, well, we label these two forces as M1, 2 and M2, 1, right? Those two forces, same magnitude, opposite direction. If you add them together, because M12 equal to negative M21, this is Newton's third law pair. M1 provide force on M2, meanwhile M2 provide force on M1. So if you add them together, this is 0 because the same magnitude, opposite direction. And the force is a vector, so you can always add them together, right? And the same magnitude, opposite direction, so add them together equal to 0. Okay. So those two forces are internal force. So add them together always equal to 0 if they interact with each other. So internal force always, if you add them together, always equal to 0. Okay. So net force equal to net force here, we only consider the force from outside, only consider external force. If net force on a system is 0, which means external force, net external force to a system is 0, then you have momentum conservation. Okay, momentum conservation means the total momentum of this system, this assume this is initial, and then their interact with each other, right? So this is M1, M2, M3, right? So this guy move to here, V1I, V2I, and V3I, okay? And right, so when they this initial final M1 here, M2 reach there, M3 reach there, assume, right? So this is the final velocity. 3 V3F, V2F, okay? If the force, net force from outside add all together is 0, then you have momentum conservation, which means total momentum here equal to total momentum here. So total momentum there is M1 V1I plus M2 V2I plus M3 V3I equal to final momentum M1 V1F plus M2 V2F plus M3 V3F. Okay, so that's the meaning of momentum conservation under one condition. If net force on this system is 0, and that net force only consider the force from outside, external force. Okay, that in that case, momentum conservation. And here actually is what I'm talking about, right? So this is the final momentum. You add all the momentum of the elements inside of the system, okay, and equal to all the momentum before. That is initial momentum, right? So final momentum P F total, okay, equal to Pi total. Okay, so that's the meaning. So that's a conservation of momentum for a system of objects. Okay, so how about one object, right? So this is one object, right? For this one object mass, right? Well, if net force on this object is 0, okay, right? Which means delta P over delta T is 0, so delta P is 0, so momentum conservation, right? So MVF equal to MVI, right? And if you cancel M on both ends, so VF equal to VI, which means V is constant. Okay, so let's go back to Newton's first law. If net force equal to 0, velocity is constant. If this object doesn't lose any mass, right? So mass is constant. For some problem, mass is not constant, right? So we will see that problem later. So same thing for a group of objects, right? For a system of object, right? You have a momentum conservation if net force on this system is 0. When you calculate net force, you only calculate the force from outside. So if this object, right, there is a force on this object. Okay, it's not between them, not in within, right? So there's a force on this object, and there is a force on this object. If you add those three forces, right, are considered as external force. So this F1, F2, F3. If those three forces add all together equal to 0, then you still have momentum conservation. Even you have net external force, but if you add all the external force together equal to 0, you still have momentum conservation. Okay, here's an example about momentum conservation. Okay, so there's a boat, right? You have two boats. Okay, the two boats stay at rest, right? So not suddenly, just at a certain moment, right? This guy push on another boat. Okay, so in this case, you consider this as a system, right? So what's the total momentum before? Momentum before is both of them stay at rest, right? So it's 0. Then this guy push on this boat, okay? So what is the final momentum, right? If you do this, so this boat move to this direction, right? And this boat will move to that direction. Okay, final momentum is m1 v1f plus m2 v2f, right? Okay, and final momentum equal to initial momentum. Why? Because there's no external force applied. This guy provide a force here, right? Meanwhile, this boat provide a force on this guy. Okay, so this guy push this boat 2 in the direction with a force 46 Newton, and meanwhile this boat push back on this guy with the same magnitude of force opposite direction. Okay, 46 Newton. So well, by the way, this is considered as internal force, right? So it's just net force is 0. Okay, so we have momentum conservation, and based on that, we can tell this equal to 0. So v1f and v2f they must in the opposite direction. So add them together, you can make it 0. Okay, so this is one kind of example. Give you m1 and m2, you can figure out what is v1f and v2f. Okay. Well, if you give you v1 the velocity of this boat, you can figure out the velocity on that boat. Okay. Same thing happened as recoil, right? So if you shoot an object, okay, okay. So this gun, and then there is a bullet inside, right? So, well, so we consider gun and the bullet system, right? So this is this initial momentum. Before you pull the trigger, initial momentum is 0. Then you pull the trigger, right? So what happened here is this, okay? Gun and the bullet, right? Pull the trigger, bullet move to that direction. What will happen to the gun? Gun will move to this direction, right? So final momentum is also equal to 0. Final momentum means momentum of the bullet plus momentum of this gun add together equal to 0. So gun must move in this direction. Actually, it's not only gun, right? You and the gun move to this direction because you pull the trigger. Okay, so gun move to that, bullet move to that direction. So you add all the momentum together equal to 0. Okay. Well, why usually you don't move? Actually, you move, right? The shoulder move back a little bit. Because, well, if you hold just use the gun, right? Just use the hand, your hand to hold the gun, right? So when you pull the trigger, bullet move forward, the gun and your hand will move backwards. Okay, that's the recoil. Okay. Um, Same thing here. There is a bomb. Okay, right? So before the explosion of the bomb, momentum is 0, right? And then explode, right? So assume this bomb separated into 3 parts. Okay, so separated into 3 parts, right? This one V1F, V2F, and V3F. Okay, now this is M1, M2, M3. Okay, and so final momentum equal to 3p's, right? Momentum of the 3p's add together. Okay, M1 V1F plus M2 V2F plus M3 V3F add all together equal to 0 because initial momentum equal to 0. Okay, and well, this is a two-dimensional problem. So you have to build X and Y to solve this. Okay, we will deal with this kind of problem later. The point here is this, momentum conservation. So this is before explosion, this is after explosion. Okay, there is no external force applied to the system. Explosion, it comes from within. Okay, now we talk about collision. Okay, collision problem. So what's the collision? Two objects striking one another. Okay, two objects, right? Striking. So they bump to each other. Okay, so this is called a collision. In general, collision time is very short. Okay, short time, short enough, right? So the time is short enough. And because the time is so small, you have a huge interaction between them, right? Okay, interaction. Because time is very short, any force outside can be ignored. External force, because time is short, so the internal force is big. So the so so any force from outside compared to this interaction is small, so we can ignore the external force. For all kinds of collision, we can classify them into 2 kinds: inelastic collision and elastic collision. So inelastic, okay, and elastic. Elastic means energy conservation. You don't lose any energy. Inelastic means you lose energy. Okay, for inelastic collision, you also there is a very special case. It's called a completely inelastic collision. Okay, we think that elastic collision we think this in elastic collision, object will stick together after they bump each other. Okay, um, so we will look at this kind of inelastic collision first. So completely, also we call that perfect inelastic collision. Okay. Here's an example of completely inelastic collision. You see there are two cars, right? Railroad cars. So this is a one M1 move with V1I, alright? Then M2 move with V2I. Then they bumped each other, right? So after they bumped each other, they connect with each other, okay? So move with the same velocity. So this kind of collision, we call that perfectly inelastic collision, okay? So for any collision, because the collision time is very short, so we can ignore the force time short. So uh, the force we think or internal force is very big, so we can ignore the external force. So when you ignore the external force, right? So net force is zero, right? So you have a momentum conservation, okay, which means Pi equal to Pf, okay. So for this system, you have momentum conservation. What is Pi? Pi is m1 v1I plus m2 v2I, and Pf equal to m1 plus m2 vf. Okay, so this is the equation. And if give you v1I, v2I, right? So this is the initial momentum, this is the final momentum, and just use this equation. Okay, we can figure out what is the velocity after they bump together with each other. Example, well, let's plug in some data, right? So M1, assume is 1000 kg, and this is 1200 kg, okay? This is 5 meter per second, right? So this is 3 meter per second. And final, right? So 1000, 1200, and we want to know what is the VF, okay? So based on momentum conservation, right? So assume this is a positive direction, okay? 1000 times 5 plus 1200 times 3, right? Equal to 1000 plus 1200 and VF. Okay, so VF is 5000 30 well 1200, right? One more, 3600 divided by 2200, right? So this is what, 8600 divided by 2200, right? So this is about a little bit less than 4, 3.9. That's 3.8. Yeah, about right. Okay, meter per second, right? Positive means they move in this direction. Positive direction. Okay. All right. We can use this. We can solve a lot of problems just by using this momentum conservation. Here's another example. So you have a ballistic pendulum, right? So this is a pendulum. Okay. Okay, ballistic pendulum, and there is object, right? Hit this pendulum, and then the object will stay inside of this pendulum, right? And then there's swing to this height. Okay. Um, by using this method, right? So we can observe how high this pendulum swing, right? So from VF to here, you have from this side, right? So you have energy conservation. Okay, and then from energy conservation, we can figure out what is the final velocity, right? And then you can figure out from final velocity, you can figure out what is initial velocity is. Okay, so this actually is a method to measure speed of a bullet. Okay, uh, so how to use the energy conservation, right? So here you have only kinetic energy, 1/2 m, capital M plus small m, right? Vf squared, and then you swing to this height, right? You only have potential energy, m plus m gh, right? So you assume this is a zero height. Okay, here velocity equal to 0. When you swing to here, you stop. Okay, so you have velocity equal to 0. So from this equation, we can tell Vf equal to square root of 2gh, right? So m canceled, right? And then you can go back to figure out what is the initial velocity, right? So the bullet hit this pendulum, right? Velocity pendulum. Before and after, you have a momentum conservation. So before, so Pi equal to Pf. And this collision is perfectly inelastic collision. So initial momentum is mvi, right? And final momentum is m plus m vf. Okay. So from this equation, you can figure out what is the vi. Vi equal to m plus m divided by m vf. So plug into this equation, m plus divided by m 2gh. Okay, so by looking at how high the ballistic pendulum swing, this h, right, you can figure out what is the speed of the bullet. Okay, so that is how you figure out the speed of bullet. Well, that collision is the one dimensional collision. This also can apply to two-dimensional collision. Example here is there's a car, okay, travel with 16 meter per second towards east. Another car travel with 20 meter per second towards north, and then they bumped each other, right? So this is what happened. And then immediately after they bumped each other, they stick together, move to the same direction. Okay, so well, it turns out this is a two-dimensional problem. So you have momentum conservation. So Pi equal to Pf. Okay, so m1 v1I plus m2 v2I equal to m1 plus m2 vf, because they stick together, right? Well, assume we know v1, v2, and the magnitude and direction, right? And then this is two-dimensional problem. We use components method to deal with a two-dimensional problem. So we build x and y. If this holds, which means you use components, right? Which means m1 v1I x plus m2 v2I x equal to m1 plus m2 vfx. Okay, so this is on x-axis. Okay, well, because we know v1i, v2i, right? So this is we know v1i, v2i, right? So we know their components, x components. Actually, only v1i, this guy has x component, this guy has no x component, right? Similarly, you have okay, so this is for y-axis. The components in y-axis also conserved, right? So from this equation, you can figure out what is vfx. This equation, you can figure out what is the vfy. Okay, anything else is known. then you can tell what is, so what is the final velocity Vf equal to square root of Vfx squared plus Vfy squared, right? So this is the magnitude of the final velocity after they bump to each other. And the angle here is inverse tangent function of Vfy over Vfx. Okay, so you can figure out what is velocity, final velocity and direction, right? So we talk about this a lot. So for two-dimensional problem, deal with the components method, right? So you look at the components. So this equation you can decompose into two equations, one in x-axis and one in y-axis. Okay, that's all for the inelastic collision. Okay, so now let's talk about elastic collision. So what is elastic collision? Elastic collision, other than momentum conservation, you have energy conservation. Here we only talk, well, energy, right? So we talk about, during the collision. So energy conservation is kinetic, mainly deal with the kinetic energy, right? All right. So you have two conservation, momentum conservation, energy conservation. Okay. So here is an example, and let's talk about one-dimensional first, right? So this is a one-dimensional elastic collision, maybe elastic, right? Energy conservation, momentum conservation. Okay, so here's an example. You have two objects, M1 move towards right with velocity v0. M2 initially stay at rest. Okay, and then they bump to each other. Okay, and that collision is an elastic collision. After collision, M1 move with 1f, v1f, right? M2 move with v2f. Okay, so if we know M1, M2, and v0, we can figure out v1f and v2f. Because you have two unknowns, right? We have two equations to deal with. Momentum conservation. Okay, so m1 v0, this is total initial momentum, equal to m1 v1f plus m2 v2f, right? This is one equation. Second equation here is energy conservation, m1 v0 squared. This is total kinetic energy before, total kinetic energy after, m1 v1f squared plus m2 half m2 v2f squared. So you have two equations to deal with, right? So this is the second equation. Well, right? So let's figure this out, because this is so what do we do here is this. First, we energy conservation, right? So we cancel f on everywhere, half on everywhere, right? So that's the second equation. So what do we do here? So we, for this particular problem, we make some change of the equation, right? So for the first one, from 1, right? So if we move the m1 on left side equation, so m1 v0 minus v1f, okay? I can take this arrow bar on top of that away, because the one-dimensional problem, use a positive and negative, you can figure out the direction, okay? So right side is m2 v2f, okay? So this is from 1, you get this 3, right? From 2, you can just move m1f, v1f to the left side, right? So m1 v0 square minus v1f square equal to m2 v2f square, right? And this you can further factor them. M1 v0 plus 1 vf, v0 minus v1f, right, equal to m2 v2f squared. So this is equation 4. Okay, next what you do here is you let 4 divided by 3. Okay, so what you get here is 4 divided by 3. So this is 4 divided by 3. So left side divided by each other, right side divided by each other, right? So you have a V naught minus, so left side, if you divided that, so you can have V naught plus V1F on the left side. Okay, because M1 cancelled, and V naught minus V1F cancelled, right? So left side you only have V naught plus V1F. Right side, right? Same thing here, M2 cancelled, and V2F cancelled 1, so you have V2F. So this is 5. Okay, and then you plug V2F into, you plug 5 into 3, into, not 3, into 1. Okay, well, actually into, let's plug into 1. So what we have here is M1 V naught equal to M1 V1F plus M2 V2F, right? V2 is V naught plus V1F. Okay, and then you just reorganize them, rearrange them, right? So you like M1 V1F, M2 V1F, right? So because we want to solve V1F, okay, let's further down. So what we have here is, okay, M1 V naught equal to M1 V1F plus M2 V naught plus M2 V1F, right? So directly from, open up this parenthesis. Okay, and then we bundle this V1F together, right? So V1F together. And then V1F equal to, so move this to the other side equation, M1 minus M2, okay, V naught divided by M1 plus M2, okay? So it's this one. So this is equation, right? And then what is V2F? V2F, right? We know V2F equal to V naught plus V1F, right? So V naught plus, this is V1F, right? So M1 minus M2 V naught, right? So this equal to 1 plus, you factor out V2 naught, V naught, right? So this one equal to M1 plus M2, M1 plus M2 plus M1 minus M2 V naught, right? So M2 cancelled, 2 M1 plus M2 V naught. Okay, so we got this equation. All right. So does this make sense to you? So if M1 is much bigger than M2, okay. So what happened here is, just consider M1. This one is much heavier than M2, bigger than M2. Consider this is metal, okay, and this is plastic. Okay, so the mass will be totally different, right? So if that happens, if in that case, what will happen? Consider this is a bowling ball. This is M2 is a ping pong ball. So bowling ball with velocity hit the ping pong ball. So in your mind, you can tell ping pong ball will move faster forward, right? Bowling ball will move almost no change of velocity. Okay, so we can come back to here. If M1 is much bigger than M2, so V1F equal to, okay, so because M1 is much bigger than M2, right? So it's almost M1. Bottom is M1, right? So because you can basically ignore M2 because M2 is so small. So this is V naught. What is the V2F? V2F equal to 2m1 m1, right? You can ignore the m2 v naught equal to 2 v naught. Okay, so that's what happened. So if m1 is much bigger than m2, that will be happen, right? So bowling ball move forward with initial velocity. Ping pong ball will move with double velocity forward. Okay, so let's consider another case. Another case here is what if um, what if um, what if m1 much smaller than m2. Okay, so in this case, ping pong ball hit with bowling ball. Okay, bowling ball stayed at rest, right? So what will happen? Uh, by intuition, we know ping pong ball will bounce back. Bowling ball almost no motion at all, right? Or bowling ball hit a wall, right? Ping pong ball hit a wall, ping pong ball will bounce back. Wall will just like no change, right? All right, so if that happens, we know V1F equal to, well, M1, ignore that because so small. M2 V naught, right, equal to negative V naught. V2F equal to M1 so small, so 0. M2 V naught equal to 0. You see, bowling ball stay at rest and the ping pong ball bounce back. You see, velocity is initial, it's opposite direction of the initial velocity. So that's about right. In physics, we always like to use extreme condition to verify if the solution is right or not. Okay. All right. So that's it for one-dimensional. How about two-dimensional? Two-dimensional, same thing. We have to uh, we have to bump in. We have to use the components method. Okay. So the example here is this: you have an object, right? Bump to another object, but this is not head-on collision. It's a glancing collision. It's called glancing. Glancing, right? So you bump each other with an angle. Okay. So all we know here is this guy's initial velocity. We know the initial velocity, right? And we know the mass. But we want to figure out, so after collision, that's what happened. M1 move to this direction, right? M2 move to this direction. Okay. So unknown here is we have this is unknown, angle here is unknown, this is unknown, right? We have some knowns there. Well, figure out that, right? So so if we know, well, let's see how many equations we can have. So if this is elastic collision, two-dimensional, right? So here's what we know. Momentum conservation. Momentum conservation, VI equal to PI equal to PF, right? So in this case, you have to use vector notation, right? So M1V1I plus M2. Well, M2 V2I V2 because V2I is 0, so let's just ignore that because this guy is 0, right? Okay, so total initial momentum. Final momentum is M1V1F plus M2V2F. Okay, all right. Well, we know some angles, right? So this V1F, we know the angle of V1F. We don't know the V2F, we don't know the angle, right? So this equation, we can separate into two equations, X component and the Y component, right? So we find the X component, okay? So X axis, okay? And the Y axis, and then we just figure out the components. M1, okay? V1I, you only have X component, right? So V1I, and you only have X component, right? So let's just plug in the data. M1 times 1.50, right? Equal to M1 V1F, and look at the x component, right? So this is 0.610, and angle here is cosine 66.8 degree, right? And plus M2, excuse me. Okay, so V2F, right? So this is M2, x component, V2F cosine theta, right? And the y-axis you have, well, initial momentum is 0, right? You don't have y components, right? So y-axis 0 equal to y components, right? So this is M1 V1F, right? Magnitude, and then sine. So V1F is actually 0.01 sine 66.8 degree. Actually minus, right? M2, and we use this angle, right? So the components in y-axis, right? So this is a V2F sine theta. Okay, so let's see. In this equation, we have this is unknown, this is unknown, right? If m is unknown, let m1 equal to m2, right? But they don't know, so it's m. Okay, so this is unknown. So you have three unknown, two equation, you cannot solve that. One more equation you have here is energy conservation. Okay, so m1v1I square equal to 1/2, right? 1/2 m1 v1f square plus 1/2 m2 v2f square. Okay. Well, assume m1 equal to m2 equal to m. Okay. So you have three equations, three unknowns, and then you can solve the equation. You can solve them. Okay. So this is unknown, right? Theta is unknown and m is unknown. So three equations, three unknown. Momentum conservation, energy conservation. So you can solve this problem. Okay. All right. So now let's talk about other topic. Here is the center of mass. Center of mass concept is very important. So if we talk about system, right, we want to know where is the center of mass. What's the meaning of center of mass? Center of mass here is this. If you have two objects, right? So center of mass is the point where the system can be balanced in a uniform gravitational field, right? So this M1 and M2. You have to find a point. Assume M1 and M2 linked by a very lightweight bar, okay? And if you want to balance the system, you have to find a point so that the bar is balanced, okay? So if M1 is very massive compared to M2, so that point is towards M1. If M1, M2 the same mass, then the point will be in the middle. Same thing here. If M2 is more massive than M1, the point will be very close to M2. Okay, so that is the center of mass. We call it a CM. Okay, well, mathematically, right? Mathematically, center of mass of this system, okay, the x, right? Center of mass, x-axis. So assume this is the x-axis, right? The x coordinates of center of mass equal to m1 x1 plus m2 x2 divided by m1 plus m2. So the position of m1, okay, and the position m2, they put together. Okay, so this is mass and position, then divided by the total mass of the system. Okay, so that is center of mass in the x-axis. Same idea, we can figure out, well, what is the y-coordinates of center of mass? So m1 y1 plus m2 y2, m1 plus m2. Okay, so here's the equation, and m1 plus m2, you can also use total mass, okay, to represent that. Okay, so basically this is weighted position of the mass, okay, that is the center of mass. So center of mass always close to the more massive object, okay, so that's how you calculate center of mass. Well, center of mass, so that is x coordinates of center of mass, right? And also same way, you can figure out what is the y coordinates of center of mass and the z coordinates of center of mass if you have three-dimensional problem here. And center of mass, not necessarily within the object, okay? So this is the book, center of mass will be the geometry of the book, right? So if this book is homogeneous, okay, uniform, and this is a sphere, center of mass is in the middle, right? Okay, and if a donut, right, where's the center of mass? Is here, it's the middle, and the middle, nothing in the middle. So center of mass can be on the object, can be outside the object. Okay, so if you have a bar, okay, where is center of mass? Center of mass should be somewhere here, right? It's outside of object. Well, if we know concept of center of mass, right? So from the equation, right, center of mass, right, x component, then we can tell what is. So total mass times the center of mass, right, equal to m1 x1 plus m2 x2. Okay, and if you have position change, okay, within time delta t, if center of mass, right, move from one position to another position, so delta xcm, right, equal to m1 delta x1 plus m2 delta x2. Okay, so if you have position change within delta t, and then you can tell m delta xcm, this actually is your displacement, delta t equal to m1 delta t plus m2 delta x2 delta t, right? This position change, displacement over time actually is velocity, right? So velocity of center of mass equal to this part, addition of all the velocity, right? M times the velocity divided by total mass. Okay, same derivation. What's the acceleration of center of mass? Acceleration equal to everybody's acceleration times mass over, add all together over the total mass. So for the system, you have a lot of objects, right? So they move randomly, but you can always use center of mass to represent the motion of the whole system. Okay, and based on Newton's second law, right? You see center of mass times acceleration. Acceleration we calculate here, right? Equal to the net force on this system. Net force is external force. Because internal force always cancel each other, right? So you look at the external force. Okay, so So example here this, right? So you have a rocket, right? Then this rocket, if you shoot a rocket, right? Let the rocket go, right? Shoot out, then you have some explosion, okay? After, what happened after the explosion? After the explosion, everything will have free fall, right? So you see, got here, everybody have a free fall, okay? And then free fall, and then just like that, right? So what happened here is center of mass, okay? Center of mass will follow Newton's law, will have a trajectory motion, okay? And then center of mass is a combination of all the particles. Okay, so all the particles can go anywhere. However, if you look at, you add all the acceleration times mass all together, that is the motion of the center of the mass. Center of mass will follow Newton's law. Okay, center of mass will go through the trajectory motion. Anything else, why you can go randomly, doesn't matter, but add all together, that is center of mass. Center of mass will follow this trajectory. Okay, um, that is what happened to the center of mass. Center of mass, it turns out a very huge concept in physics. So path of center of mass, very simple, just uh, um, this parabolic path, right? Okay, and anything else, if you trace someone, something, right? Something will, just like follow any kind of path, but center of mass will go through this. We learn from chapter 3, chapter 4, yeah, projectile motion. This is the projectile motion. Okay, last slice of this whole chapter, we talk about changing mass. Okay, so what happened? Changing mass for rocket propulsion. Okay, so this is what happened. You have a rocket, okay, in space, and you move forward, right? So how to move a rocket? How to let a rocket move forward? Rocket has to ejection mass out of it, right? So assume ejection of mass is delta m, okay, and those mass move out with speed v, okay, and so for this rocket you have momentum conservation, right? So total momentum before assume is 0, right? Total momentum after is, well, you eject this kind of mass out with v velocity, right? And then, well, let's see, make this a positive direction. Okay, this is the final momentum, right? Plus rocket minus delta m, right? Okay, and then you have v prime forward. Okay, well, let's rewrite this. Total momentum before is 0, and after momentum is you have a mass out. Okay, plus m minus delta m, capital M, right? V prime. Definitely the V prime will be in this direction, positive direction, right? Okay. So what happens here is this: you push out this much mass with the velocity, right? And so this is a momentum change of the masses, right? This is a momentum of, so for the whole rocket's momentum change, right, is you push out this much mass, okay, times v, okay. So momentum, so this is rocket, right? So you have momentum, you get rid of this much momentum, okay. Total momentum is 0, right? So you get a much this momentum. So the momentum change for the rest of the rocket will be same as whatever momentum you push out, okay. And this momentum you push out, if you divide by time on both end, right? So this is the force from the main body of a rocket to this part of a mass, right? equal to delta m delta t times v, speed you push out those masses. Okay, so that's the force for the main rocket on those fields, right? Meanwhile, those fields will push back a force. Okay, that force we call it a thrust. Rocket move forward based on this thrust force. Okay, so this thrust force basically is changing mass over time. Okay, it depends on how quick you push out those masses, so you can move forward. So that is the thrust force. Thrust. So that force push the rocket to move forward. Usually you push out the mass with the constant speed. Okay. So that's all for this chapter. All right. So make a summary. So that's what we learned. We learned linear momentum. Okay, and the Newton's second law by using the momentum impulse momentum theorem. Okay, and we also talk about momentum conservation. Okay, momentum conserved if external force is 0, and internal force always is 0 for the system, right? So then we talk about collision. We have inelastic collision and perfectly inelastic collision. And then we talk about elastic collision. There's inelastic collision and elastic collision. Okay. So elastic collision. And the last we talk about the center of mass. Okay. And this equation talk about center of mass, y coordinates, right? So velocity, acceleration of center of mass. Okay. And the Newton's law on centers of mass. And then we talk about propulsion, rocket propulsion, thrust. The force push rocket forward is actually this equation. It depends on the how the time the changing mass, the time rate of changing mass you push out of the rocket. That is the force. Okay. All right. Sorry for the alarm. I will handle that next time. All right. So I already post practice exam on Blackboard, and I will post exam on Blackboard soon. So other than study chapter 9, you need to take care of the exam. All right. So this week you study chapter 9 and take care of the exam. So next week we'll talk about chapter 10. All right. See you next time.